Hey everyone, welcome to our very last video for our Math 15 course, where we're going to do some examples using the ANOVA process. So remember, ANOVA is a hypothesis test that allows us to compare three or more means by comparing their variances. So first example, we're looking at number 65 in the chapter 13 homework. And it says a grassroots group opposed to a proposed increase in the gas tax claim that the increase would hurt working class people the most since they commute the farthest to work. Suppose that the group randomly surveyed 24 individuals and asked them their daily one-way commuting mileage. The results are shown below. Use a 5% significance level. Test the hypothesis that the three mean commuting mileages are the same. And you can see here, we have, let's scooch this up just to make sure it's out of the way. We have 8 data points in each column, 3 columns, 1 for working class, 1 for professionals with middle incomes, and then 1 for professionals who are wealthy. And it shows us the mean commuting mileages. And I'm presuming, I think it's one-way commuting mileages for each of these individuals in the samples. And it says perform a hypothesis test, and we're comparing 3 means. So seeing that information, that's what tells me that I'm doing ANOVA. As I see test the hypothesis. So I know it's a hypothesis test with an alpha of 0.05. And then it says 3 means. And the only method that I have for doing that all at once is with ANOVA. So I know that I'm doing ANOVA. And I know for ANOVA, at some point, I need the data in my calculator. So before I start this process, I'm going to enter the data in a calculator so that I can clear this screen and get some room to work. So let's clear out that underlying, and I'm going to do this first example with the TI-84. So I know to enter data, I need to go to Stat, Edit, and I need to clear out any data that's already there. And then just start typing. So first column is going to be the working class data. And then I'm going to enter the next 2 columns. I'm going to pause my video shortly and then come back once I've got that filled in. Okay, so we can see I have all of that information in my calculator. So I'm going to minimize that for a second and clear off our workspace here and start our hypothesis test. So p-value method, step 1 is stating our hypotheses and identifying the claim. Step 2 is going to be p-value. Step 3 is going to be our decision, and step 4 is our conclusion. We decided we're doing an ANOVA test for 3 means. So the null assumption is that all 3 groups are equal, and that number labeling corresponds to the order that I saw them in the table. So that first column was working class people, second one was middle income professionals, and third column was the wealthy. For the alternative, all I have to do is state at least one mean is different from the others. And then to identify the claim, I'm going to go back and skim through that problem. And that last sentence says using a 5% significance level, test the hypothesis that the 3 mean commuting mileages are the same. So they're saying test the claim that all the means are equal, which is the null. That's going to affect how we phrase our answer in step 4. The upside for p-value, the function call is the same. I just need to say ANOVA, and then parentheses, and then the list names where I put my data. And I'm going to put that up here. I put my working class data in list 1, the middle income data in list 2, the wealthy in list 3. So L1, L2, L3. And notice They're in the same order that they were where I listed them in the null. That's good practice. Once you've decided an order 1, 2, 3, be consistent with it. So let's pull up our calculator and run that function call really quick. So stat test all the way to the bottom. And this is a little different. It doesn't provide you with prompts, but we know it's asking for those list names. So to call list 1, I go second 1. And I'm going to use that comma, which is right next to the parentheses, and then second 2, comma, second 3. List 1, list 2, list 3, and then I'm going to close those parentheses and hit enter. And just like everything else, it spits out a test statistic and then a p-value. And you'll notice it's calling that test statistic F because we know this is an F distribution test. But we're just going to record that p-value, which is 0.0014. If you scroll down, there's some more data. There's factor and error. Factor, you'll notice that BF is 2. That's the number of groups minus 1. You'll notice error, that degrees of freedom is the total sample size, which was 24, minus the number of groups, which was 3. And then they have this SS and MS value. If you were going to perform further tests to locate where the difference is after you've done ANOVA, you would need some of that information. However, we're not going to do that in this class, so we don't need anything other than the p-value from this menu. If you're interested in what that looks like, you can drop by office hours and I can kind of go over 2 of those tests. They're called the Sheffy and Tukey tests, but we're not going to cover them in this class. So we're finished with our calculator. Now we just need to finish our hypothesis test. So step 3, we make a decision. We compare that p-value to the given alpha, the level of significance. And we're told 5%, 0.05. 0014 is less than or equal to. So we can be fairly confident that we can reject that null. And then we're going to think back to our last video. I reject the null, so there is enough evidence to. And then going back to step 1, I look where the claim is, and the claim is the null. So I'm talking about reject or do not reject. There is enough evidence to reject the claim that. And then I go back and I look for wording in the problem that summarizes the claim. Test the hypothesis that the 3 mean commuting mileages are the same. So the claim that the 3 mean commuting mileages are the same. So based on this hypothesis test, I am confident that there is a statistically significant difference between one of those means and the other 2. I don't know which one is the different one. It's possible all 3 are different from each other, but I don't know where that difference lies. So in this case, this is where I need to go to one of those alternative tests to locate where the difference is. But we're content with ANOVA. We know that these 3 means are not all the same. So at least one group has a higher or lower commuting mileage than the others. Okay, let's try another example. So this one says the data shown are the weekly admissions in millions of people attending movie theaters over 3 different time periods. At a 5% level of significance, is there a difference in the means for the weekly attendance for these time periods? So we've got 1950 to 74, 75 to 90, and 91 to 2000. And then we have millions of people. So this is weekly. So for 1 week in 1950 to 1974, 58 million people attended a movie theater. 1 week in the 91 to 2000 era, 23.3 million people attended the theater, and so on. They're asking us, is there a difference in the means for these 3 time periods? And looking at this data, I have a sneaking suspicion there is, because I can see in the 1950s, there's 2 really big data points at the beginning. I can see in the 1990s, there's fairly consistent in the mid 20s, and that the 70s to 90, a little lower. I've got values in the teens. So looking at the data, I suspect there's a difference. We want to statistically demonstrate that it is significant. And to do that, we're going to use ANOVA. This time I'm going to use GeoGebra. So let's pull our GeoGebra window up. And let's clean it up a little bit. It still has some stuff from previous videos in it. So I need 3 lists, 1 for each. I'm just going to call them A, B, and C. And I just enter those values separated by commas. And then we're going to call ANOVA, and it's going to spit out our p-value when we're ready to go. I'm going to leave that blank for a minute so we can start our hypothesis test. So that was the opposite of what I wanted. Let's clear us some room to work here. Just like before, we need our null and our alternative. We need our p-value. We need our decision, and we need our conclusion. So the null, we're comparing 3 different time periods, the 50 to 74, 75 to 80 to 90, and then 90 to 2000, 91 to 2000. So mu1, mu2, mu3, and then at least 1 mean is different. In this case, it says, is there a difference in the mean? So the claim that we're testing is the alternative. Next, we're going to pull back up our GeoGebra to run that p-value command. And I know that it's going to be ANOVA. And my list names, and I named them A, B, and C. And somewhere I should indicate what A, B, and C represent. I need to know what data I put where. So this was the 1950 to 74. This was 75 to 90. And this was 91 to 2000. So let's pull that window back up. And we see 2 values. We see a p-value, and then we see a test statistic. So in this case, our p-value is 0.1928 rounded. So we're going to make our decision by comparing that p-value to our alpha. And our alpha is 5%, so 0.05. And 0.19 is bigger than 0.05. So we are not going to reject the null. Meaning, yes, we saw some differences in the data, but based on how variable those samples were, we're not confident that that difference in the samples is statistically significant enough for us to consider the population means to be different. To summarize, first starting with the we did not reject, so there's not enough evidence. And then looking up at step one, our claim was the alternative. So we're talking in terms of support. There is not enough evidence to support the claim. And then we summarize the claim from the word problem. There is not enough evidence to support the claim that there is a difference in the means for the weekly attendance for these time periods. Because I am simply going to circle that. And that is what you would put here as your summary for the claim. There is not enough evidence to support the claim that there is a difference in the means for the weekly attendance for these time periods. This example is important because it shows us even when we're looking at our data by eye, it's tempting for us to declare, yes, based on that sample, there's a difference. But if that data is really variable, it's still possible that the population means are fairly close together, and it's going to be hard to locate a difference. So remember, we're comparing means by looking at how variable those samples are. And these samples were fairly variable, particularly that first group. And so there's not enough evidence to support the claim that those population means are different based on this sample data. Okay, let's run one more. Our last example, a research organization tested microwave ovens. At a 10% level of significance, is there a significant difference in the average prices of the three types of ovens? So here we see 1,000-watt microwave ovens, 900-watt microwave ovens, and 800-watt microwave ovens. So I'm going to label these group 1, group 2, group 3. I'm going to start my hypothesis test over here by stating my hypotheses. The null is that those three mean prices are equal. And then the alternative is that at least one mean is different. I'm going to shortcut here, diff. And then the question says, is there a significant difference? So the alternative is our claim. Our next step is p-value. And we know that we use the ANOVA function call. I'm going to use our TI-84 again. So list 1, list 2, list 3. And I'd like it if you paused your video for a second, grabbed your calculator and bound that. I'm going to do the same, and I'll be right back with a response. So you can see here, I have all of that data in data tables, and you can see that those lists are different lengths, and we can see that in the data table we were given. There's 2 more values in the second and third column that weren't in the first, and that's okay. It's okay if the 3 groups we're comparing have different size samples. I'm going to run the ANOVA call, so stat test ANOVA. I've got 3 lists, list 1, list 2, list 3. And I get a test statistic of 10.1 and a p-value of 0.001. So from here, I can make my decision. For step 3, we compare our p-value to our alpha, and our alpha is 10%, which is 0.10. And 0.001 is way less than 0.1. So we can confidently reject the null. Our last step is to write our conclusion. So let me clear some room for us to do that. I'm actually going to type this. So our conclusion is here, and looking at our decision in step 4, we rejected. So there is enough evidence. And then looking at our claim in step 1, we claimed the alternative. So we're talking about support. There is enough evidence to support the claim. And then we go back and we look at the statement in the problem. Is there a significant difference in the average prices of the 3 types of oven? So we would say there is enough evidence to support the claim that there is a significant difference in the average prices of the ovens. So this is another instance where we've found a difference. And we would, again, if we wanted to locate where it was, we'd have to go back and run another test comparing each of those groups pairwise. So if I want to compare those differences, I've got 3 different types of ovens, the 1000 watt, the 900 watt, and the 800 watt. I'd have to perform 3 tests, 1 versus 2, 1 versus 3, and 2 versus 3. Again, we're not going to do that, but this is an idea that could be used with some of the previous methods that we've used to test pairs of means. That's something to think about. That's kind of cool. My hope is that after those examples, you feel a little more comfortable with ANOVA. I'm hoping it's like the least scary of the hypothesis test. This is definitely the one where the calculator does the most heavy lifting for us. If you have questions on anything this week or about the class in general, feel free to send me an email or drop by office hours. Otherwise, I will see you in the forums.